Hi, my name is Melis Onur. I'm a first-year electrical and electronics engineering student in Bilkent University, and this is a video presentation for my Physics 101 course lab project. My aim in this project was to measure the moment of inertia of a solid, uniform sphere. This sphere, to be precise. In order to do this, I used the principles of the conservation of energy. I made a setup using an inclined plane and a spring. In my setup, I also used a ruler for measurement of length and a wooden block to ensure that the sphere would go as linearly as possible. I was going to use the spring to calculate the final velocity of the sphere. However, the software that I used for data analysis already gave me the instantaneous velocities. Therefore, the spring was deemed redundant, so I did not use it. First, I measured the mass of the ball, its radius, and the inclination angle of the plane. Then I started letting the ball go from different heights on the plane, and I recorded all of this procedure with my mobile phone. Afterwards, I used that footage to analyze the movement of the ball and take the data that I required. In rolling motion without slipping, the point of contact with the floor is only momentary, so the friction force does not do any work. Writing the conservation of energy, I find an equation to find the rotational kinetic energy, which is dependent on I, the moment of inertia. Since I let the sphere go without rolling it, the initial rotational kinetic energy is zero. Leaving the rotational kinetic energy alone, I find myself a good equation to calculate the moment of inertia. As a condition for rolling motion without slipping, the angular velocity has to be equal to linear velocity over r. So in this equation, all of the values except for I are measured. In order to measure the change in position and the change in velocity, I uploaded my footage to a data analysis software. With that, I put some data points manually on the ball. I made it so that all the data points were as close to the center of mass of the ball as possible. Later, the data analysis software gave me the final and initial positions, as well as the final and the initial velocities. I let the ball go 6 times from different heights and followed the same procedure to get the data points to calculate the moment of inertia. Here is the graph of change in position versus time and the graph of change in velocity versus time of each of the 6 takes. As you can see, the best fit lines in the velocity time graph are almost parallel, which is expected because each time the force applied to the sphere is constant, so the accelerations are also the same. My measurements of the moment of inertia and also their margin of errors from the theoretical value are as follows. As is apparent, for each take, I had very different moment of inertia measurements and very different error margins. I believe this is due to these reasons. First of all, as I said, I put the data points myself manually on where I thought the center of mass of the ball would be. Though I cannot be perfect, and in some takes I probably put the data points more accurately than those in the other, which will undoubtedly result in some different error percentages. The second reason why I think I have so many different calculations is because of the velocity in the y-axis. You see, I tried to let the ball go as linearly as possible, but I was not perfect and the ball still had some velocity on the y-axis, which I neglected because it was so small compared to the velocity component on the x-axis. Although it is neglectable, sometimes in some takes that velocity component in the y-axis was much smaller than those in other takes, which definitely altered my calculations. The final reason why I think I have so many different calculations is because of the spring at the end of the board. As I said, I did not use the spring and I stopped taking data points as soon as the frame that I was seeing touched the spring. But again, because of the timing of the videos, sometimes the ball had only touched the spring so little and sometimes it was a little more significant than that, which plausibly changed the final velocity calculated. These are the reasons why I think I have so many different margin of errors. Here is the average of my calculations and the percentage error from a theoretical value of this average value. All in all, despite all the uncertainties in my measurements and all the random errors that occurred, I believe I have measured the moment of inertia very accurately.